The first speaker is Lingbo Wei from University of Science and Technology of China. She is currently associate professor, and she is interested in privacy problem in lightweight client. Okay, please start.
Yeah. Good afternoon, everyone. This is the outline of my talk. I will first introduce the privacy leakage problem for the lightweight Bitcoin client, also called SPV client. Then I will present our privacy-preserving lightweight Bitcoin client based on private information retrieval techniques. The performance and the security analysis of our scheme will also be discussed. The verification of Bitcoin payment requires the user to download and process the whole blockchain. Currently, downloading the whole Bitcoin blockchain requires more than 200 gigabytes of storage. The size of Bitcoin blockchain is growing very fast. Processing the blockchain imposes heavy requirement on bandwidth, computing, and storage resources of Bitcoin client. They need to fetch all transactions and blocks issued in the blockchain, locally index them, and verify their correctness against all existing transactions. Obviously, it's impossible for the resource-constrained devices like mobile phones to run a full node. So we need to use simplified payment verification, also called lightweight Bitcoin client. Full node will download, verify, and store the entire blockchain. Lightweight client only downloads and verifies the blockchain headers, which are 1,000 times smaller than the full blocks. When a lightweight client needs to verify a given transaction was included in blockchain in a block, it requires a full node. The full node will send back the transactions and the mock path that binds the transaction to the block header. This is a data structure also called SPV proof. SPV SIM is efficient now. Mobile devices can run lightweight clients and use Bitcoin, but SPV has a privacy leakage problem. Full node will know the transactions and addresses to the client's IP address and can inform a SPV client purchase habits and can effectively identify the user's real-world identity. Several solutions to protect lightweight clients' privacy are also proposed in the literature. The first one is Bloom filter-based solution. The lightweight client will insert the real keyword and dummy keywords into the Bloom filter. The Bloom filter is transmitted to the full node, and the full node will send back the transactions that match the Bloom filter. However, it has been analyzed in the paper mentioned in this slide. Bloom filter only provides very limited protection. Lightweight client can also use anonymous communication network such as Tor to communicate with the full node. Therefore, the lightweight client can hide its real IP address from the full node. But just like the title of this paper said, Bitcoin over Tor isn't a good idea. It cannot work with the Bitcoin blacklist scheme. Recently, trusted hardware-based solution is also proposed. The querying of the lightweight client is handled by the trusted hardware like Intel SGX. In the full node, Intel SGX provides a secure enclave abstract. Even the operating system cannot get the secret in the SGX. The problem is that you need to trust the Intel. And the reason we use Bitcoin is that we do not want to trust anybody. In this paper, we propose a new approach to protect lightweight clients' privacy based on private information retrieval techniques. First of all, we have a simple observation. The problem we want to address is a PIR problem. PIR is a database technology that lets users to retrieve information from a database without revealing which information in the database was queried. In our problem setting, the SPV client wants to query a transaction record I. It hide I by some crypto technicals and send it to the full node. The full node will process the query. and send back the query result with knowing I. The database here is public because the Bitcoin blockchain is public. What we want to hide is the access pattern, which transaction the client is interested in. So it's a PIR problem in the crypto literature. There are two kinds of PIR in the literature. Computational PIR only needs one database server for the client to query. The security is based on some computational hard problem. The problem of computational PIR is that its overhead is too high to be practical. The second kind of PIR is called information theoretical PIR. We need K servers and assume that at most K-1 malicious server can load. In this paper, we only consider information theoretical PIR because it can be implemented in practice. Now we introduce the basic K-server PIR theme used in this paper. Two servers has the same database. The SPV client wants to query the false record of D here. We have two important assumptions. It's an index-based PIR. The client knows the position of the record in the database, and all records in the database have the same size. SPV client knows the position of the record. He knows the record D is a false record. So the position vector for record D is 0001. SPV client then generates K-1 random vectors. For example, here we have one random vector C1. SPV client calculates masked vector C2. C2 is the XOR, the vector E, and the vector C1. At last, SPV client sends the random vectors and masked vector to K servers. Obviously, it's a secret sharing scheme. The secret is the position vector all servers need to conclude to get E. The server will calculate and the returned record. And based on the vector, for example, the vector for node 1 is 1010, so the server will XOR the first and the third record and send back this result. When the client gets to the record R1 and R2, the client can XOR these two records and get the record D he really wants. Note the communication overhead is that the client only wants one record, but it receives K records, so the overhead is K-1 records. This basic K-server PIR is the building block of our proposed theme. However, it cannot directly used to solve our problem for the following three reasons. First, it's an index-based PIR, but SPV client does not know the index of the transaction record. SPV client only knows the keywords of the transaction. Or, for example, the transaction ID payment addresses, so we need a keyword-based PIR. Second, the transaction records have different sizes. We need PIR with arbitrary length of records. Third, the communication overhead of the basic K-server PIR is still high. We need to optimize it. This is an overview of our scheme. We have K4 nodes. Each has two databases. These bases are synchronized with the Bitcoin blockchain. We assume the server will follow the protocol. But they want to know your private information. At most, the K-1 service will conclude. The lightweight client only synchronizes with the block headers chain. It does not know the index of transaction and wants to reduce the overhead and protect its privacy. Here, we describe the two databases used in our scheme. From a new Bitcoin block, we can get a set of transaction records, including transaction and its SPV proof. We will put this transaction record into PIR blocks with the same size, so transaction record 2 may span 3 consecutive PIR blocks. Each PIR block has a transaction index, but the lightweight client does not know this transaction index. Based on the transaction database, we will construct the index database. We first get the keywords about this transaction. Then we sort the keywords and tell the lightweight client the total number of these keywords for keywords 1. We will get the lowest and the highest index of the matched transaction record and store this information in the index database. So from the index databases, we get the mapping between keyword and the position of the matched transaction record. In our theme, the lightweight client first gets M, the total number of keywords from the full node. Then the lightweight client queries index database with keyword-based PIR. At last, the lightweight client requires transaction database with a basic key server PIR. We need to use the PIR twice to complete a keyword query, so we called our theme two-step PIR. For the query of index database, the lightweight client only has a keyword, for example, the transaction ID. He wants to know whether this keyword is included in the index database. The client transforms the keyword-based PIR into log_m index-based PIR because the keywords are sorted in the index database. And the client knows M, so we can use binary search. The client first queries the keywords in the middle position of the index database. If his keywords is smaller than this one, he can query the keyword in the middle position of the lower half of the index database. Note that the client only needs to query log_m times for each query. The client can use basic key server PIR to hide his access pattern. The communication overhead of this step will be large. To check whether a keyword is in the database, the client needs to get key log_m message from the key servers because we need to query m times. So this communication overhead can be reduced by reusing randomly mixed data blocks in the previous queries, but we still need to hide access pattern, so we need to carefully design the reusing scheme. When the client finds the keyword in the index database and get to an index for the matched transaction, and the client can easily query the transaction device database with the basic key server PIR and privately get the transaction he wants. So what is the performance of our scheme? The degree of privacy protection is measured by the size of an anonymity set. The intuition of anonymity set is simple. I know you are interested in one of the transactions in the anonymity set, but I can't tell which one. So larger anonymity set is the better privacy protection. We compared our theme with a Bloom filter-based scheme. It's defined by BIP 37. Its standard solution used in current Bitcoin client. The system patterns set in the simulation are the following. We use 4 servers and 4 servers PIR, which means our scheme can tolerate 3 concluding servers. This simulation result is shown in this table. For Bloom filter themes, you can increase the false positive with the Bloom filter to enlarge the anonymity set and provide better privacy protection. However, the communication overhead will also increase because the client will get many useless transaction records. Compared with our scheme, with almost the same communication overhead, our anonymity set is almost 300 times larger than the provided by BIP 37. Therefore, our scheme can achieve better privacy communication trade-offs. Here is the conclusion of my talk. Thank you for your attention.
So for this paper, We will not have the Q&A session because of her flight schedule. So if you have any question, please email her. Thank you.
Thank you.
So our next speaker is Muhammad Enes Imtiaz. He's from Boston University, and he's currently a second-year PhD student. And the author is identified the effect of churn on the Bitcoin network.
Hi all, I'm Anas and I'm a second-year PhD candidate at Boston University. This work was co-authored by Professors David Starobinski and Ari Trachtenberg and Nabil Yunus, who just graduated from Boston University. So in this research work, we asked two questions and we basically try to answer them. The first question is, does there exist churn in the Bitcoin network and to what extent? And the second one, how does churn impact the Bitcoin protocol? This presentation is structured as outlined here. It is mainly going to be divided into two parts. In the first part, I will define the notion of churn, the previous work that has been done on Bitcoin and churn, and then I'll describe the methodology that we use to characterize churn and the results that we obtained. And in the second part, I'll describe how we measure the impact of churn on Bitcoin, the tool that we developed, and the results that we obtained. So when a new transaction is created in Bitcoin, it is propagated to the peers in the network who then add their transaction to their mempools, and some miner node then adds this transaction to a block that they create and propagate that block to the network. By design in Bitcoin, a block is generated roughly every 10 minutes on average. And the key challenge in this context lies in basically reducing the propagation delay of propagating the block from the miner to the rest of the network. There are a few issues with slow block propagation. Number one, it can result in forks in the Bitcoin network, which results in multiple network states. When a fork is resolved, there are orphan blocks that are left in the blockchain, which result in a waste of energy not only for the miner but for all the miners who have been mining on top of these orphan blocks. Recently, an improvement was implemented in Bitcoin Core called the Compact Block Protocol, which aimed to reduce the propagation delay. There were other things that they were trying to do as well, but this was one of the things. But the question still remains, how effective is the current Bitcoin protocol in the presence of churn? Let me define briefly the notion of churn in any peer-to-peer network. In a peer-to-peer network, nodes can leave and rejoin the network at will, and the effect that is created by this independent arrival and departure is what we call churn. And like other P2P networks, nodes in the Bitcoin network are also allowed to leave and rejoin the network whenever they please. So you may wonder, like, why do we care about churn in the Bitcoin network? This excerpt is taken from Satoshi's white paper, and you can see that he says that nodes can leave and rejoin the network at will. So we can say that Satoshi envisioned that there would be churn present in the Bitcoin network, and the protocol should be resilient against churn. And you may wonder, other people must have looked at this previously. So I'll briefly go over some previous work that is related to Bitcoin and churn in the network. Apostolaki et al. Simulate partitioning attacks in the Bitcoin network, and they incorporate churn in their simulations. However, instead of characterizing churn themselves, they assume that the session lengths of the Bitcoin nodes follow an exponential distribution, but we show in this work that they follow a more heavy-tailed distribution. Decker and Wardenhofer measure block propagation time in the Bitcoin network, and they show that slow block propagation can result in forks in the network, which result in a phenomenon called information eclipsing that an adversary can leverage to mount double spend attacks. However, their work was published before the current protocol. The current improvement was implemented in the Bitcoin core, and therefore their work does not reflect the current behavior of nodes in the Bitcoin network. Neudecker et al. Studied churn from an attacker's perspective, and they show that network partitioning attacks are sensitive to churn in the sensitive to churn of the attacking node. However, in their work, they perform no characterization of churn, and thus it is unclear on what basis they choose the parameters for their simulations. And finally, Karame et al. Study security of using Bitcoin as fast payments, and they show that churn affects benign nodes and their connectivity with the rest of the network, and an adversary can leverage this to mount double spend attacks. However, they also do not cater for churn in their analysis, measurements, and experiments. And this brings us back to our first question: does there exist churn in the Bitcoin network, and to what extent? So we measure churn in the network, and to do that, we observe the behavior of nodes in the Bitcoin network. We use a network crawler called BitNodes that provides a Bitcoin network snapshot every 5 minutes. And a snapshot looks something like this. So it provides a unique host name of the node and some other information such as their location, etc. And we observe in a 60-day period that there are more than 47,000 unique nodes on the network. And this figure shows the location of those nodes. The colors here show, the green color here shows all the nodes that have been present at all times during those 60 observation periods, whereas the red nodes show, the red color shows all the nodes that have churned at least once in the 60-day observation period. And we see that out of more than 47,000 nodes, only about 1,100 have always remained on the network during the 60-day observation period, whereas the remaining 98% of the network churns at some point in the 60-day observation period. And this brief animation shows the behavior of nodes going online and offline the network. So this is just a small portion of the 60-day period, and you can see that there does exist a churn with a high degree in the Bitcoin network. And since we are in Korea, I thought it would be cool to show the behavior of nodes in this region as well. And you can see that nodes fluctuate with a very high frequency in this region as well. So we've shown that there does exist churn in the Bitcoin network. But to what extent? So this figure shows on the x-axis the churn rate, the daily churn rate of a node, and on the y-axis the probability with which a node can have a churn rate greater than the random variable r. And our experiments and our study shows that on average nodes churn with a rate of more than 4 churns per day on average. So we have all of this data, but what can we do with this? Well, we can characterize churn and try to see if we can fit a model to all of this data. But how do we characterize churn? We take inspiration from a paper that tries to understand churn in different peer-to-peer networks. And the authors of the paper state that one of the most basic properties of churn in this is the session length distribution. And in this work, we basically try to characterize session lengths of nodes in the Bitcoin network. Let me briefly define what I mean by session lengths. So imagine there is a node that stays off the network for some amount of time, and we call this duration of time a down session length. Then the node comes back up on the network and stays on the network for some period of time, which we call an up session length. And the node can go off the network again and come back on the network and continue to do this for an arbitrary number of times, where each session length may be different from previous session lengths. So in our work, we determine the session lengths of each node by checking the presence of that node in consecutive snapshots. So if a node appears in 2 consecutive snapshots, then we know that the node has been up for at least 10 minutes. Recall that BitNodes has a 5-minute resolution. And if the node does not appear in 2 consecutive snapshots, then it has been off the network for at least 10 minutes. And we try to perform statistical distribution fitting to this data on session lengths, and we noticed that prior work has shown that the session lengths are best characterized by heavy tail distribution. So in this work, we focus on fitting heavy tail distributions to the data. We use the R squared, RMSE, and visual inspection of the data to determine the best fit, the best distribution fit for the data that we have. And our analysis shows that the up session lengths are best characterized by the log logistic distribution, whereas the down session length is best characterized by the Weibull distribution. So we have the characterization of the session lengths and the behavior of the nodes. What can we do with all of this data? We can measure the impact of churn. So, but what can we measure? So in this work, we present 3 results. The first one is the number of blocks that a node is unable to reconstruct. Number 2, the number of transactions that are missing from a block. And number 3, the propagation delay incurred by the compact block failures and missing transactions. And you may wonder, like, what do you mean by compact block failures and what are missing transactions? So to understand that, let's take a look at how block propagation works in Bitcoin. So in the original Satoshi block contained full transactions where each transaction was 500 to 800 bytes. And let's take a look at how that works. So imagine this is a subgraph of the entire Bitcoin network. Node C here receives a block and it has to validate the transactions in the block and then the block itself. And once it has done that, it propagates the block to its peers, who then independently verify the transactions and the block themselves. And once they are done with the verification, they propagate the block to their peers, and in this way the block is propagated to the entire network. In 2016, the compact block protocol was introduced and implemented in the Bitcoin core, and the aim of the protocol was to reduce the size of the block by containing only a 6-byte hash of the transactions instead of the full transactions themselves. And this would reduce the bandwidth required for block propagation and in turn the propagation delay of propagating that block. However, this protocol assumes that the mempools of the nodes are somewhat synchronized, meaning that when they receive a block, they would be able to successfully reconstruct it by just looking at the hashes of the transactions in that block. However, if they cannot find a transaction that matches one of the hashes in the block, then they need to request for that missing transaction from their peer. And let's see how that works. So again, the node C receives a block B and it has to first validate the block, but when it starts to verify the transactions, it must first search in its mempool all the transactions, the hash of which would match the hashes in the block that it received. And once it is able to match all of those transactions, then it is successfully able to verify that block and then propagate it forward to its peers, who will then independently start to verify that block. However, now one of the nodes here is missing a transaction from its mempool, meaning it cannot find a transaction that matches one of the hashes in the block that it received. It will create a request for that missing transaction to its peer and send that request and wait for that peer to send it back the transaction that it has been missing. Notice that this incurs delay because the node cannot proceed with block verification until it receives all of the transactions that it has been missing. And once it has received all missing transactions, it will resume verification of the block. And once it has verified the block, propagate it forward to its peers, and then the block will be propagated to the entire network. So in our experiment, we measure the impact that this has on the Bitcoin protocol. We add 5 live nodes to the Bitcoin network. 2 nodes on the left are control nodes. They are always online on the network, whereas the 3 nodes on the left are churning nodes, and they emulate churn in the Bitcoin network. And we use the distributions that we just saw to sample session lengths so we have the down session lengths and up session lengths sampled from the distributions. And the nodes are going to churn with the down session length that is equal to one of the sample down session lengths and stay on the network with a session length that is equal to one of the sampled up session lengths. And we let these experiments run for 2 weeks, and at the end of the 2 weeks we collect our data and process it. But how do you process how do you measure the data that you need? So we study the Bitcoin core, and we insert hooks into the software, which are triggered on specific events, and at each of these triggers we record some relevant data to files. This basically shows the data that we record when a compact block is received by a node. The first line shows that a new block was received at some time from a peer with this address, but the node was unable to reconstruct the block, and it was missing 1200 transactions that it sent a request for to its peer. And when it received the missing transactions from its peer, it was able to successfully reconstruct the block, verify it, and then propagate it forward. And finally, I'll present the results that we obtained. I said that in this work we present 3 results, so let's look at them one by one. So the first result was the number of compact block failures that a churning node observes. So this graph shows on the x-axis our 5 nodes, and on the y-axis the number of blocks that they received. The green bars show the total number of blocks that they received during the 2-week experiment. The blue bar shows the number of blocks that they were able to successfully reconstruct, and the red bar shows the number of blocks that they were not able to reconstruct. We see that the control nodes were able to receive more blocks, which is kind of intuitive. However, what is interesting is that the churning nodes fail to reconstruct more blocks that they receive than the control nodes. On average, the churning nodes are unable to reconstruct roughly twice as many blocks as the control nodes. Second, we'll look at the number of transactions missing from a block. This figure shows the number of transactions missing from each block that all of the 5 nodes were unable to reconstruct. Notice that the y-axis is a log scale, and we see that the control nodes rarely miss more than 10 transactions in a block that they receive, whereas the churning nodes usually miss up to 1,000 and sometimes even more transactions in a block that they receive. And this figure shows on the x-axis the number of transactions that are missing in a block, and on the y-axis the probability with which a block is missing more than n transactions in a block. And we can see that the churning nodes miss more transactions in a block than the control nodes. And on average, a control node misses less than 3 transactions in a block, whereas a churning node misses more than 300 transactions in a block that it receives. And finally, we'll look at the propagation delay that is incurred because of the missing transactions and the compact block failures. This graph shows on the x-axis the propagation delay in milliseconds, and on the y-axis the probability with which the propagation delay of a block is greater than the random variable t. And we see that the churning nodes have, on average, more propagation delay than the control nodes. And our experiments show that the churning nodes have a 135% more propagation delay than the control nodes. And finally, we measure the propagation delay of blocks that the control nodes were able to successfully reconstruct, but the churning nodes were not able to do. And we can see clearly that the propagation delay in those blocks is much higher, where the average propagation delay of a block in the control nodes is less than 100 milliseconds, whereas the propagation delay of a block in a churning node is more than 1 second. And the greatest propagation delay that we had in our data set was more than 40,000 milliseconds. In conclusion, we have studied the presence of churn in the Bitcoin network, and we have shown that it is present. We have characterized churn, and we hope that this characterization can be used in future work which involves churn. We have measured the impact of churn, and we have shown that churn does impact the efficiency of the protocol, and we have seen large propagation delays on a single hop. And depending on the diameter of the network and the churn rate of nodes in the network, this propagation delay could be quite high. And we believe that some future work can be done in this perspective. The security implications of churn in Bitcoin network could be studied, specifically the viability of a double spend attack. And we have seen that the number of transactions missing in blocks are quite high. So we propose that a possible improvement could be an intelligent synchronization that keeps the mempools of the Bitcoin nodes somewhat up to synchronization. Finally, we have made our log system open source, and it is available on GitHub. And all of our experimental logs are available on our lab's Git server. And with that, I thank you all for listening to my presentation and look forward to your questions.
Okay, any questions?
Yeah.
When you were measuring churn and propagation delay, did you happen to look at how that affected orphan rate in the network at all?
We did not look at the orphan blocks because we did not have the data for that, but we do plan to look at that in the future. Yeah.
Hi. When you measured how long nodes spend online versus how long nodes spend offline, was there any correlation by node? Were nodes that were offline for longer periods also online for longer periods, or were they independent?
There was very random behavior. There were some nodes that only churned once, like they would stay online for roughly like not half, but more than half of the 60-day period, but then they would go offline and never come back on. There were nodes that would fluctuate more than 10 or 20 times during a single day. So there was very random behavior that we observed by the nodes.
Okay, thank you for the presentation. So our next speaker is Hans Walter Behrens from Arizona State University. Currently, he's a PhD student. So he's interested in block propagation for Bitcoin network. And paper title is Velocity Scalability Improvements in Block Propagation through Rateless Erasure Coding.
All right, thank you. Before I get started, I do want to make a special thank you to the Dash Community Treasury, whose financial support made this research possible. This is a very good segue to the previous speaker, so hopefully if you paid attention to that one, this one will be also very interesting. So we've heard quite a bit at this conference about the benefits that we get by having a trust-free system with permissionless public blockchains, and also about what we have to give up as part of that, which is generally performance, the transaction throughput of the network relative to a centralized system. This is what's sometimes called the blockchain scalability problem, and there have been many, many attempts to solve this in the literature. So rather than confirming a block every 10 minutes, you might make a change to a consensus protocol or use a different proof that allows you to reduce the amount of time from 10 minutes to, say, 10 seconds. Another approach might be breaking the transactions across multiple chains using sharding and then bringing those into synchronization somehow. On Tuesday, we saw a very good tutorial about Lightning networks, payment channels that allow you to take transactions off of the main chain and reduce the amount of throughput that you actually need to get good performance. But one of the simplest and most obvious ways to get more transactions through the network is to simply use bigger blocks. Bigger blocks means you can fit more transactions. So why don't people do this? So one of the main problems of using bigger blocks is when you have more data, it simply takes more time for that data to propagate across the network. And as we just saw from our previous speaker, as we increase that propagation time, we have all kinds of problems that crop up from that. In particular, that longer propagation time means that we have higher orphan rates. And higher orphan rates means we have more soft forks, potential chain reorganizations, and a lot of undesirable behavior within the network, as well as inefficiency in mining. Additionally, when we're working with public permissionless blockchains, there's always going to be an incentive for Byzantine non-cooperation. If there's a way for the participants to violate the rules of the propagation protocol in a way that benefits themselves, they'll do so to get that benefit. And last but not least, there's a very fine balance between the transaction fees that are gained from the transactions that are actually included in the block and the block reward itself. And those are tuned to the individual chain. And by increasing the size of the block within a particular network, those balances can be thrown off. So given those constraints, what does our protocol aim to do? Well, we want to maximize throughput of the propagation between nodes. So if we increase the size of the nodes, we need to make sure that that propagation happens relatively quickly. We also need to cap the orphan rates, because if orphan rates get too high, not only is the network less efficient, but if the orphan rates exceed 50%, then there's never going to be consensus in the network and the whole thing falls apart. We also need to balance the transaction fees, the mining fees, with this new increased block size. Finally, we want to be able to maintain the existing security guarantees that we get from the mining process itself. So I'm going to go over the background a little bit quickly because we got a lot of this from the previous speaker. But one of the key ideas that's commonly used is the idea that you don't need to send the whole block. Rather than sending the whole block, you only send the missing pieces. And we heard about compact blocks already. There are a few other proposals like extreme thin blocks, graphene, that follow a relatively similar concept where the missing transactions are detected and only the missing transactions are sent, rather than sending the entire block. That's very good, but as we heard, when mempool synchronization is not very good, that doesn't work as well. And that's because the Bloom filters or the invertible Bloom lookup tables, essentially the false positives that you get from those probabilistic data structures make it difficult to determine which transactions are actually missing, and then you lose the ability or you lose the efficiency gain that you would get from this approach. So when those fail, it sometimes is more efficient to just send the whole block anyway. The blocks themselves are propagated usually, depending on the implementation, in a peer-to-peer mechanism, similar to how BitTorrent might work, where the nodes, the full nodes, have copies of the blocks, and you can request transactions essentially from the nodes around you or blocks themselves, and the pieces that you're missing are sent to you. It's also a good fit for the public permissionless blockchain paradigm because it's mostly decentralized as far as peer discovery is concerned, except for the initial bootstrapping process. On the other hand, the Merkle tree validation doesn't take place until you have all the transactions. And if you send an intermediate layer, like you might in BitTorrent, for example, with the torrent file, you can do a little bit better, but it's a similar problem, and then you have to figure out how to get those intermediate hashes to the other nodes as well. But more importantly is you face what's called the coupon collector problem, which is that if you are missing a particular piece of your data, you need that specific piece from someone else in the network. And if there's no one there who can give it to you, you just have to wait until that piece is available. That's the problem that you face. You know, if you're torrenting a file and just that last segment is missing, and you just can't find a seeder who can give it to you. Okay, so how do we build on that? How can we improve on that? So the key idea that we used here was the concept of rateless erasure codes. These are also sometimes called fountain codes, but you can think of them kind of as network coding meets Reed-Solomon codes. So you take the data that you're trying to share, in this case the blocks, and you divide that data up into chunks, k chunks, and that data is then encoded along with metadata about which chunks actually were used to generate the particular symbol into this data structure, which is called a symbol. And then you send that symbol to a recipient. Now this process is randomized, so you can generate symbols continuously from the same source data, essentially endlessly. And every symbol will be unique, but they will still somehow be related to the original data. Then your recipient receives these symbols, and once they've received k prime symbols, they can reconstruct the original data with some probability, some high probability. And k prime is generally not very much more than k, usually only about 102%. So the overhead is pretty low. So how does that work from the perspective of the Bitcoin network? So the miner discovers a block. It generates the header and the symbols and sends those to some node, the first node in the network that it's propagating the data through the network. That node then notifies its peers that it has a new block in its inventory. And if any of those neighbors don't have that block, they can request symbols for that block. Not only from the node that they received the inventory request from, but all of their neighbors. If that request comes in and the block is unknown to the nodes, the request is dropped. Otherwise, if it does know, it will start generating these symbols and sending them to the receiving node. The receiving node collects these symbols from the peers that are feeding it, and when it has enough symbols to reconstruct the block, it notifies its peers with a received message saying, okay, I have enough, you can stop sending me symbols now. So that's great, but how does that play in when we have adversarial nodes? Well, there are a couple things that an adversarial node can do. They can start asking their peers for non-existent blocks. That doesn't really cost anything to mitigate because it's essentially the same as asking for a node that a peer hasn't heard about yet. So those are just dropped, and we don't really have to concern ourselves with those. A node might request symbols from a peer and then never send the received message and just try to tie up the bandwidth that way. But thanks to the characteristics of the rateless erasure codes themselves, there's actually a cap on the amount of data that we can expect a particular node to need. So if they receive more than, let's say, 102% of the size of the block, we know, okay, either the received message was lost in the mail somehow, in which case, okay, fine, I'm going to stop sending messages anyway, or this node is doing something nefarious, and I'm going to give them a little demerit and keep track of which of my peers are not behaving properly. Now, the third thing that they can do is actually the most tricky thing to detect, and that's when you request symbols from your peers, and they start sending you symbols back, but they're not actually symbols from the data. They're just garbage that the peer has been generating. And the way that we mitigated this was by storing the symbols as node symbol pairs in a tensor and keeping track of which symbols came from which nodes. Then we can see, okay, well, we received this symbol from node A, and we received this symbol from node B, and the decoding process tells us that these symbols are incompatible. There's no way that these both can be valid symbols, which means either A or B is doing something nefarious here. But it's difficult to determine between which one is the nefarious node. So it's fine, we'll just wait until we get symbols from C, and eventually we'll be able to rectify that. The downside is this is relatively memory intensive. So you can do things like sample among your peers or things like that, but that's a way to mitigate that. Okay, so what kind of results did we see from this modification? So we implemented this in C++ on top of Dash, since they were funding the research, using a particular implementation of fountain codes called libraptorq. But we found that it was very difficult to get realistic, heavy workloads using real-world testnets. So we ended up having to extend an existing simulator to measure both the network latency and throughput so that we could measure the actual propagation of the blocks, but we also wanted to track the individual node mempools and the block discovery process so that we could measure things like how mempool synchronization affected the propagation process and where blocks were coming from and things like that. The transaction workloads that we used were actually taken from the actual Dash ledger itself so that we could have kind of a realistic workload setting. As far as block sizes are concerned, we started at 100 megabytes and we went up to 1 gigabyte. We kind of wanted to find the maximum size that could possibly be supported under this paradigm. And the chunks that we broke the data into, we tried 10 chunks all the way up to 10,000 to kind of see what the behavior was. The encoding and decoding process for the rateless erasure codes is just relatively efficient. It mainly only takes XORs, and it's strictly dominated by the propagation process itself. So we didn't evaluate we didn't explicitly measure the time for the encoding and decoding. So the first thing that we looked at was propagation time. So when you get up to a 1 gigabyte block and you don't use anything, it will essentially never finish propagating. It will just go forever, which is about what we expected to see. And even when you use blocks of 10, it's still pretty long. Again, essentially will never finish propagating. But when you start breaking it into smaller and smaller pieces, you can actually get pretty relatively low propagation times, even for very large blocks. Now, 160 seconds is still pretty long relative to the 10-second propagation times at most that we just saw. But that's also for blocks that are significantly larger than what's currently supported. So what kind of effect does that have on orphan rate? So as the propagation time increases, there's an exponential relationship with orphan rate. So it's very important that we not let that orphan rate or that propagation time get too high. So from the results we saw, essentially larger, more chunks were more effective in terms of reducing that propagation time, but that there still was a pretty significant effect in terms of the propagation time and therefore the orphan rate. Finally, what did that look like from the perspective of block size? So this shaded region here represents the 50% orphan rate beyond which consensus of the network will break down. Now, this leaves aside the sort of efficiency question of miners mining blocks that will potentially have a relatively high probability of being orphaned. And we do have a sort of economic model in the paper, if you're interested in that, to show where it actually makes sense economically from the miner's perspective to mine under this new sort of paradigm. But from our results, we found that you could get to about 500, even 600 megabyte blocks while still maintaining that orphan rate below 50%. So, in conclusion, the velocity protocol pretty significantly improves the scalability of block propagation within the network. We can detect and block adversarial behavior in a way that doesn't degrade the security guarantees that we previously had under the old propagation paradigm. It also increases the winner-take-all effects for miners because the blocks are larger, they have more transactions, therefore they're worth more in transaction fees, and they're potentially more would be mined less frequently, potentially, depending on the transaction workload. That would be tuned by the chain itself. Consensus can be maintained up to about 600 megabytes, but optimal miner revenue is about 300 megabytes, we found. And also, it's important to note that this protocol can be used alongside existing improvements. You don't have to sort of take this over, for example, graphene. They can be used in conjunction. So when the mempool synchronization is good, you can just take the transactions that you're missing. But when mempool synchronization becomes quite bad and you need to get the whole block, this might be a good solution for that. So thank you so much, and I look forward to your questions.
Okay, thank you for presentation and questions.
Hi, so one question I had was, why did you use fountain codes? Like if you use like a more traditional error correction code, let's say that expands the K blocks into, let's say, K parts into, I don't know, K 1.1K parts, and then commit them into a Merkle tree, you can avoid that adversarial solution, right? Like, how are you familiar with the work on data availability in Ethereum? They use, erasure codes as well.
So the mechanism by which the fountain codes are implemented is actually very similar to that, depending on the implementation. But I'd be happy to dig into it a little bit more deeply with you offline after this, if that's okay.
Okay, let's thanks to our speaker. So next speaker is Christian Grenflo from University of Waterloo. He is currently PhD candidate, and this is the last paper of this technical session. In this paper, many optimization techniques for hyperledgers are introduced. So the title of the paper is FastFabric, Scaling Hyperledger Fabric to 20,000 transactions per second.
Okay, thank you for the introduction. Last paper, let's do this. After the two last speakers talking about permissionless blockchains, now we jump to permissioned blockchains. For this work on FastFabric, I collaborated with Stephen Lee from UMass and Professor Golub and Professor Keshav from University of Waterloo. So first question is, why do we even care about scaling Fabric up? So right now, usually permissionless blockchains range in fast blockchains range in the transaction throughput of hundreds transactions per second, and Fabric can deal with 1,000 to 2,500 transactions per second, dependent on what kind of system you have. But if we compare that with more traditional use cases, as we heard yesterday as well, for example, Visa, depending on the most recent information, has to deal with more than 50,000 transactions per second in peak times. So there's quite a gap to like traditional database applications, and it would be nice to close that gap at least somewhat. So before I get into our optimizations, I will quickly refresh your memory on how Fabric actually works. So the Fabric network is divided into several roles. So all the nodes that replicate the state and the blockchain are called peers. And a subset of these peers execute smart contracts in Fabric called chain code. And these peers have the endorser role on top of the committer role. And then, apart from that, there is an ordering service who is solely responsible for ordering transactions and putting them into blocks and then disseminating it into the network. So how that works is a peer has a transaction that it wants to get into a block. So it sends this transaction to a subset of endorsers in the network, and all of these endorsers execute the smart contract, attach the results to the transaction, sign it, and send it back to the client. The client makes sure that all these endorsers get the same results, collects the signatures, and if it has enough signatures, it will send this transaction to the ordering service. And if many clients do that, the ordering service will collect a whole bunch of transactions. And if it has enough, or if a timeout occurs, all these transactions after ordering will be bundled into a block. And this block will then be disseminated to all peers, who can then notify the client that the transaction is on the blockchain. So what we did is we forked the Fabric code and then dug deep to see where we can improve it and make the whole system faster. Our goal was to leave all the APIs intact, to essentially don't do anything that would disturb existing applications or make it in any way different than it is currently, so it's all under the hood improvements. Let's start with the orderer. So a little bit deeper under the hood, the client sends the signed transaction to the orderer, and there the orderer has to first check that the transaction is actually readable and that the client has permission to send transactions. So there's this whole processing step. And then in our case, we use the Kafka consensus. So after the check, it will send the transaction off to Kafka, which does the actual ordering of the transactions, and then it waits for the queue to come back and creates blocks from the ordered transaction that it receives back from Kafka. So what we found out is that Kafka is not a very good tool for data dissemination, which means that it cannot deal with large message sizes, and by large in this context I mean in the order of kilobytes. So what we did is we split off the transaction header and only send off the IDs to Kafka, let it order the IDs and keep the transaction on the orderer. And then you receive an ordered queue of transaction IDs and reassemble the transactions and put them in a block and then send it off. And then the second thing that we found out is that the order is mostly single-threaded here. So when it receives a block from the client, it will do all the checks, send it off to Kafka, and only then it will get the next block from a client. So in order to speed that up, we split up the process part here. So we have a single thread that is just there to receive transactions as fast as possible from the client, put them all in a buffer, and then we can parallelize the processing of the transaction. Keep in mind that Kafka is the orderer here, so it doesn't really matter in which order the processing is done, as long as they are all valid and then sent off to Kafka. So we have these two improvements for the order. First, the transaction header split, and then the pipelining and parallelization of the processing. On the peer, we will also first look on the under the hood going on that we have here. So a peer can have two roles. It can be just a committer or endorser. So it needs to be able to endorse transactions that a client sends in. And it also needs to deal with blocks that are delivered from the ordering service. So there are 3 steps involved for the commitment process. The first one is again similar to what the orderer does. It checks that the order server that sent the block is actually allowed to send the block and is a valid orderer. That it can actually read the block and all the transactions can be unmarshaled and so on. And if that is correct, it will then check that each transaction has proper signatures and enough endorsements. And only if all these steps are valid, then the transaction will be committed to the block. And here again, and the commitment is done in 2 steps. One is we have a log of the ledger, which is essentially put into the file system and then indexed. And the other part is we have a copy of the world state, so all the keys and that are currently on the ledger are stored in LevelDB, which is a key value store. So the first thing that we looked into is how much work can we actually put onto other machines that is not essential for this critical path. So the first thing is that having a blockchain, having a key value store behind it is kind of an overkill, because you get the consistency, guarantees, and redundancy already from the blockchain. So you don't need all this overhead. So let's just throw it out and replace it with an in-memory hash table. Now you have a problem if your peer actually goes down, because then all your state is gone. So at some point you really need to persist it somewhere, but you might as well put that onto a different server and just send off the block after it's validated and say store it. Which has the nice side effect that now you actually don't care how this server stores the data anymore, and you might as well store it maybe in Postgres or Spark and do analytics on top of it. So that is one role that we encapsulated and put on a different server. The other thing that we can do is do the same thing for the endorser. So the endorser, in order to execute the smart contract, needs access to the world state. So we actually need to replicate the hash table onto the endorser. But you can just do a simple update here that it sends every time a new block is validated. And otherwise, the endorser is completely independent of the process. So we've freed up a bunch of resources now on the peer. But the problem is that so far, this process is single-threaded. So a new block comes in, it's verified, the transactions are validated, and then it's committed. And then only then you go on to get the next block. So what if we could do something similar to what we did on the order and just take as many blocks in as we can? So we have here, of course, the problem that we have a blockchain, and so we need to actually commit it in the correct order. But the verification step and the validation step don't depend on the order. So here you only check that you can read it and the signatures are valid and so on. So they don't depend on each other, and you can do all of that in parallel. So I will show you a little bit of an animation here on how that works. So all these gophers that you see here represent Go routines, which are essentially lightweight threads. And what we did is we have a single thread, again, as on the ordering service, that takes in blocks as fast as it can and puts it into a buffer. And this buffer is then, the blocks are taken out by a pool of Go routines here. And the important thing is that at this point, only the thread that took the blocks in knows about the sequence of the blocks. So it actually needs to communicate the proper order to this gopher down here that is eventually responsible for committing all these all these blocks. So these gophers here can verify the blocks all in parallel, and maybe block 2 is the first one to succeed. So the next pool of Go routines will pick that up and validate, split it up and validate all the transactions that are in the pool in parallel. So we have a pool of gophers here, and maybe it uses about 80% of the pool. And at the same time, block 1 now was ready to validate, and it will also be, the transaction in block 1 will be validated at the same time, but it can only take up about 20% of the resources. And so block 2 is finished first again, but now this gopher down here has a problem because it cannot commit block 2 because it still waits for block 1 to finish. So what it does, it stashes it away and still waits for block 1 to finish. So in the meantime, block 1 could take all the available resources, finishes fast, and is actually delivered to the commit gopher down here. Now it can commit it to the database, and it takes out the block 2 out of the stash, can it commit it to, and then waits for block 3. And then the chain continues. So we have taken all the work that we can encapsulate and put it onto different servers. We have then used up all the resources that we have on the server by parallelizing as much as possible. So what else can we do to speed it up? Well, do less work. So it turns out, because of the modularity of Fabric and the nature of how the blocks are delivered to the peer, is that it uses gRPC and protobuffers to unmarshal the bit stream into proper objects again. But these block objects are highly hierarchical because there can be many different types of blocks. And so on every level of this hierarchy, you essentially have byte arrays that you then, dependent on the situation, have to unmarshal again and then go deeper, unmarshal again, and so on. And what Fabric does is it doesn't care about the result and just for the next step sends off the byte array again, and depending on what that step has to do, it needs to unmarshal all over again. So what we did is we actually store all these unmarshaled objects in a cache, and whenever the next step after the verify block step, the validation step might need the same object, so it just asks the cache, give me back that object, and I don't need to compute it all over again. So taking all these improvements together, we've done 5 things. Separate the transaction header out and only send the ID to Kafka. Then pipeline the messaging on the order. Take the block storage and the endorsement out to different servers and parallelize the validation step. And then lastly, aggressively cache all the computed work that you do on the peer. So that's all nice in theory, but let's see if the results back it up. So due to timing constraints here, I will only show you the most important results, but in the paper we have a lot more benchmarks than I show you here. So this work was based on Fabric 1.2, and because we really wanted to focus on this critical path of validation and commitment, we kind of reduced it to this. So all the benchmarks here are really just ordering and then verification, validation, commitment, and gossip and so on is all deactivated, so it's not a full-fledged system. We tested it on 15 servers, which are relatively standard stats here with 2.1 gigahertz. Each of them has 24 hardware threads and 46 gigabytes of RAM, and all of them are connected with a 1 gigabit switch. So you see we have one server as a client, and then the minimal setup for an order, which is a single order, and then 3 Kafka servers, 3 Zookeeper servers. And the peer is split up into this fast validation and commitment peer, then the storage server, and we show here that we can actually scale out multiple endorsers for the same peer, so that the same peer replicates the state onto multiple endorsers, and all of them can then endorse based on the same state. And so you can scale the endorsement and the commitment independently. For our test runs, we send 100,000 transactions per second to the network, repeated that 100 to 1,000 times, depending on how long the test ran. And the chain code that we used is a very simple one that we just send $1 from one account to another. And we made sure that all of these transactions are not in conflict with each other, because from a performance standpoint, this is actually the worst case, because you have to do all the checks and eventually commit it. An invalid transaction would be thrown out of the pipeline at some point earlier. So to have a baseline, this gutted system of 1.2 without any optimizations was tested, and we got about 3,180 transactions per second. And now let's see the results. So here for the order tested independently, we have quite an improvement. The optimizations here are cumulative, so O2 includes the results of O1. And most importantly here is the typical message size for a Fabric transaction is about 2 kilobytes. So we can speed that up from about 6,200 transactions per second to 21,700 transactions per second. And we get a similar result for the peer. So here, the results get the system from 3,100 transactions per second to over 21,000 transactions per second. And at the same time, we can see that the latency on the peer actually goes down. We have a small bump here where we see the parallelization overhead, but that is mitigated by the unmarshalling cache that we introduced with optimization 3. So lastly, we tested an end-to-end simulation here against the base result of Fabric 1.2. And here we get close to 20,000 transactions per second with our improved system. And since we submitted these results for the conference, I re-implemented our improvements for Fabric 1.2, the current 1.4, the current release. And in this case, it's actually a full-fledged system. So it works just like any other Fabric implementation would work as well. So you can just spin it up as you would Fabric 1.4, the release candidate. And here we get slightly lower numbers, but as you can see also in the base case, because it has to do gossip and all these other overhead mechanisms that it does. And we get to 14,000 transactions per second with our improvements, which is the same improvement factor that we got before, just have the additional overhead. So in conclusion, we improved Fabric by a factor of 6 to 7 from 3,000 transactions to 20,000 transactions per second. We achieved that by reducing the I/O that Fabric does, maximize the parallelism, and introduce more efficient data structures. And lastly, we did aggressive caching on the results that were computed. And I invite you all to check out the GitHub repository where I uploaded the code for both FastFabric and FastFabric 1.4. And for 1.4, you have actually instructions on how to run it, and it's quite easy to do, and you can run a full Fabric network with all the improvements built in. Right, with that, I thank you for the attention and happy to answer any questions.
Thank you for the presentation. Any questions?
Hi. Unfortunately, I think this might be more a question about Fabric than about your work, but I guess I'm unclear on why it's okay to validate blocks in parallel. It seems to me that the things going on in one block might depend on which things had happened before them.
So I kind of glossed over that part. So the validation step that is shown here is really just checking that the transactions are properly formed and that the number of endorsements are correct and so on. And in the commitment step, you actually have the sequential execution of the key rewrite sets where it actually matters that you do them in sequence, because then key versions might depend on earlier versions. Yeah, correct. Because Fabric executes before ordering. All the results have a version number. And if you have a conflict there, you need to check that in sequence. Otherwise, you get a conflict for different peers. So this validation of the results needs to be part of the commitment step and be sequential. Otherwise, you don't have consistency.
Theoretical, the speed, the speed up, what you try to do here. What do you think that, what is sort of a real bottleneck here over there theoretically, and what do you think that, how much we can even speed up, the afterwards?
So you mean how we can speed it up from here?
How you figured out what is the sort of a bottleneck here
Oh,
for
I see.
the speed up?
Okay, so we did extensive benchmarks and call graph analysis. So we looked at, we ran the system for hours and see where does the system spend most time, and then looked at those parts and tried to improve that. And so first we saw that it takes a lot of time to write to the hard drive, and then we saw that the unmarshalling takes a lot of time, and so we eliminated one hotspot after the other. And right now the ones that are left are actually allocating memory and the cryptographic analysis. So we might go with a hardware accelerated cryptography solution in the future to further increase it.
You talk about in the validation side or order side or client?
That is on the peer, yeah. So the commitment side. So you can, the clients can be scaled up independently because you can have any number of clients. The endorsers, we showed that we can scale them now independently. So if you need more servers that execute the chain code, then you just spin up more and the state gets replicated to them. So the two things that need to be looked at are the ordering service and the peer. And as I said, for the peer, right now the biggest bottleneck is the crypto. And on the ordering service, we're looking into different consensus algorithms to speed it up as well.
Yeah, just for the double checking of that, you mentioned that the cryptographic validation, that is actually, you said, can be parallelized. Right?
Mm-hmm.
That's what you're trying to do here, right?
Yeah, so essentially we parallelize multiple blocks and multiple transactions at the same time, as much as a single server allows. But still, cryptographic comparisons are expensive, so that is the biggest bottleneck that we still have.
Okay, and my last question is about the impact of the ordering consensus algorithm. Right now, it is just Kafka.
Yeah.
It is just, it doesn't do anything in there. So if we use the raft is also, it doesn't do for the Byzantine fault.
Right.
If we go Byzantine fault consensus algorithm, what do you think that you can do? You can apply for that also?
So the parallelization on the peer doesn't have to do anything with the consensus algorithm. So it's more of how fast can we get a Byzantine fault-tolerant consensus algorithm. So our group in Waterloo has preliminary work on a consensus called Canopus, which at the moment is still crash fault tolerant. And there we got actually 5 million transactions per second independent of blockchains, so just the consensus. And we're building, right now we're working on making that Byzantine fault tolerant, which will definitely decrease throughput by a lot, but we're hopeful that we get at least 100,000 transactions after we've done that work. But yeah, time will tell.
Okay, any questions? So I have a question. So in your framework, you use the cache. So is there any possibility to see the invalid value of the cached data?
Sorry, what was that?
Cached data.
Mm-hmm. What about the cache data?
So if you see the cached data, is there any possibility to see if the cached data is not valid?
Because the block data between validation and commitment never changes, it can either be unreadable, which gives you an invalid transaction, or it can be readable, and then in that case it's valid from the point of data corruption, I guess. But then you still need to check that the logic is valid. So I'm not quite sure what you're asking for.
Oh, yes.
Yeah, because you are the last presenter here, I want to have one more question. Because you are presented here the performance of the Hyperledger fabric, what do you think that in terms of compared to the generic permissionless like EOS, can you compare in terms of the performance, how much the fabric can be overcome, that
So,
the EOS?
Yeah, permissionless systems right now still have the problem that all the existing consensus algorithms are just too slow. So they're kind of bottlenecked by the consensus. So if we get a better consensus that can speed things up, then I'm sure that also permissionless systems can be much faster than they currently are.
Okay, no more questions? Okay, let's thank to the last speaker.